last class we were talking about performance evaluation, metrics for performance evaluation and so on. Let us look at one case study, right, for trying to determine some common metrics. Okay. So the system that we are looking at is comparing a set of congestion control algorithms, right. Congestion control should be familiar, I should not be explaining that to you, right, because the background says networks is preferably there. So so I have a set of links which make up a path, and there are several intermediate routers along this path from source to destination, and the routers can forward the packet or sometimes drop the packet and so on, right. So and then in this network system we are trying to look at how can congestion control be better supported, right. So there are, let us say, 3 or 4 systems that you want to compare, and so the objective or the service of the system is, right, congestion control is a service offered, right, and in general as part of forwarding services, right. So as part of the network's packet forwarding services, right. So in general network forwards packets, but sometimes it wants to be more intelligent when it forwards packets, therefore there is some mechanism for doing congestion control. Okay. And when you transmit a block of packets, so when a block of packets is sent from the source to destination, right, few things can happen in terms of the outcomes, right. There are some possible outcomes in such a system. So one is the packets are delivered, right, either in order or out of order. That is true in any packet switch system because packets can be switched out of order, therefore there is one possible outcome. Then there are some packets that will be dropped by the one or more of the intermediate routers, right. So packets can be dropped, anything else, any other outcome? So either delivered in order, out of order, or not delivered at all. Yesterday we saw one more option, or Friday we saw the other option, right, that the packets can be delivered but error, right. So so that is your 3 options, right. So this is the basic definition of a system, because you are trying to see how we can be sort of methodical, right, in trying to list out all the potential performance parameters for a given system.
Control mechanism will look whether it is an error or error free.
No, it will not, but as far as the service is concerned, because the user uses the network to send packets from point A to point B, at the end of it the packets could be in error because of link errors, right. Either it is dropped because of buffer overflow or because of wireless link errors.
Which is defined is only congestion control.
Yes, the service as part of the network forwarding services, right. So I am trying to compare different congestion control mechanisms where forwarding is the basic service. On top of that I am adding this congestion control as an extra service, right. And yeah, so congestion control does not really have anything to do with erroneous packets, but still as part of forwarding sometimes errors can take place, right. Congestion control will usually deal with result in one of these two, whatever mechanism you use. Packets can be out of order because the congestion control mechanism decided to hold a packet and send some other packet ahead of it, right, or dropping is simply because the buffers got full or close to full, right. Yeah. But as a network service these are the possible errors, right. Okay, so now we should try to come up with a set of possible performance metrics that will try to capture the performance of such a system. Okay, so possible metrics. So we have some of this we have seen in the advanced networks course too, right, but some of you have not, but you have at least taken the undergrad networks course, right. So the common metric, right, that we know is the packet delay, right, so response time or delay. Or the packet that is the high level metric. So some of these are local to the user, some of these are global to the system as such, right, or okay. So then another metric we are now look at throughput, right, so you can look at a router and look at how many packets per second is the router able to handle, right, that either system throughput or per router throughput, right, whichever wherever you measure, right, you can look at every router and look at the throughput of each router, or just look at the entire system and say on average so many users started sending packets, I looked at number of delivered packets, and therefore the total capacity in terms of packets delivered is X number of packets per second, right, that is something that we can do at various levels, right, so the granularity of this can be varied. Then other things, okay, processing time per packet, right. This is algorithm dependent, right, it depends upon the forwarding algorithm as well as the congestion control algorithm.
So can you get drop probability?
Yes, yeah, that will essentially come, right, as we look at other things, yes. Within the response time also we can look at just the mean of the packet delay, or sometimes also variance, right, variability in terms of packet delay. So we can look at this, we can make that even, right, so variability in response time, which is technically related to this one, it is not a separate metric, but just to be in sync with what the book has, I will list that as another metric, right, variability in then others are packet drop probability and so on, right. So it is a fairly straightforward exercise. So since packets are dropped, I need to measure, right, what is the fraction of packets that are dropped, yes.
So you look at the queue length as well.
There is one question.
Sir, when we were talking about the throughput, number of packets per second, is it the number of packets transmitted per second or received per second that you are going to calculate?
This will be usually received per second. You have the sender generates packets, packets can be stored in the network, dropped in the network, depends upon the buffer capacities, depends upon the processing time, forwarding time and so on. Ultimately you measure the total number of delivered packets, and then you look at the total delivered packets as throughput. So that you will have to define as what your throughput measure is, right, as packets delivered per second.
Yeah, I'm talking about the queue length.
Yeah. Yes. Okay. Yeah. So we will add as we go along, right. So these are higher level. Then we look at in order, right? In order delivery probability, right? I can simply count all the packets sent and then see where they all, right, sent in the same order. If it is, then I record that as in order probability. Otherwise, I will also, right, record that as out of order delivery probability. And sometimes the network also delivers packets twice, right, the same packet can be delivered twice, because what happens is this user sends the packet, it gets buffered and then it sleeps in the buffer for a long time, and then the user times out and sender times out and sends the packet all over again, right. So you might have duplicate packets being sent, so that is your duplicate packet probability.
Does that really count into the throughput part of the, because
no, you should know, yeah, that you'll have to define your throughput as saying that you will not count that, right. So only unique packets, your throughput from a forwarding point of view you will not care, you only say I have handled so many packets. When it goes to the destination, destination can say only these are so many unique packets were actually delivered, and just use that for the throughput measure, right. So that is that you have to clarify that when you write your throughput definition, that it is only right unique packets that will be considered, whereas the router itself will not know. At the router level you do not know whether a packet is duplicate or not, because the TCP sequence number is what differentiates the two packets, right. So TCP level you know that it is the same packet, therefore I will not send this packet forward.
We have given is like common for any forwarding algorithm.
True.
But
Yeah.
We are not means. Is there any specific metric for congestion control?
Okay. Yeah, for congestion. Okay, fine. Let us see if there is something else for congestion control.
Our algorithm is better from other in terms of congestion control.
True. Yeah. The congestion. Okay. This congestion control is looking like a red herring. It really makes no difference. But then let us look into what does the congestion control algorithm do, right? So now we come into business of fairness. See, that's where congestion control can actually come in. We talked about fairness, right, in the other class. So let's go here. Now this is a network level congestion control algorithm, right. So network level congestion algorithm, what are different ways in which you can try to control congestion at the network level. TCP level we know congestion window is there, right, you manipulate that to get your congestion. Choke packets can be set, right. So then the different algorithms, how do they, like in what order do they send it, or who, we will have to edit this later on, who gets more choke packets, right, how do you differentiate between the different connections. Well, one connection get more choke packets than the other one, in which case it will have less throughput, right. If I look at this throughput as I can do this per connection also, right, per connection what is the number of packets delivered per connection, and then look at the different throughputs across the different connections. That is where fairness comes in, right. Do all the connections entering the network get the same amount of bandwidth requested? Maximum fairness we will leave that for the moment, but depending on whatever they ask and so on, right, are you able to get the required amount of bandwidth, is it equitably shared among all the different connections. So that is where congestion control will specifically come in terms of how do you differentiate the different nodes in terms of how do you send choke packets, right, that is one. What other congestion control mechanisms possible? One is explicitly sending choke packets from the router back to the source nodes, right. Anything else? Yes, something like a leaky bucket algorithm, right, or doing random early detect where, or random early drop, right, where you simply drop connections, you drop packets from the, even before the buffer gets full, you sometimes tend to drop the packets, right, and that is mainly to trigger congestion control at the higher layers, but that is still a question of which connections do you trigger these drops for, right. That is where again you can look at it, you can look at these other things also, right. So you can look at right, what can we define in terms of packet drops, right. So packet drop is sort of more or less looked at here, right, packet drop probability is coming in there, and that is you can do that at the system level, at the router level, or at the per connection level, and then look at variations among the different packet drop probabilities, and that is where your fairness also will come in. Okay, so packet drop is will be taken care of by that, right, and other things are, right, so fraction of or the number of, right, choke packets. So that is to differentiate, right, in terms of which connections get more choke packets and which connections get less choke packets and so on. And the third mechanism that we use at the network level for congestion control is marking packets, right, where you simply mark the packet, we do not really drop it, you do not send a choke packet, you simply mark, say congestion bit is set on the packets, that goes to the receiver, receiver then echoes it back to the sender, right. That is again more of a gentle way of telling the network that, telling the sender that there is congestion in the network, right. So what is a marking algorithm that can also differentiate, right, and how the sender responds to that marked packet is up to the sending side algorithm, that is now at higher level, it is not necessarily at the network layer. Network layer is more of a passive observer that tells you that there is congestion and lets the upper layer decide. Okay, so this is sort of, right, sort of the standard way in which you kind of look at all the possible outcomes of the system, and then for each of those outcomes start enlisting what are the critical parameters and so on. and sometimes what people try to do is they try to combine some of these metrics together, right. See what happens is when the load is very light, right, your delay is going to be fairly low, throughput is also going to be proportional to load, right. So as your then as the load of the network increases, throughput also starts increasing, right, more packets start getting generated, more packets start getting delivered, and therefore throughput is also high, which means the queue lengths also start increasing, and therefore your overall delay is also going to be high. So sometimes people have tried to come up with their own metrics, which is say power is something that this Raj Jain and company had right, proposed as a unitary metric to look at the ratio of throughput to delay is sometimes also looked at a different metric. You compare two different systems in terms of so called power. Why they call it power? Okay, well let's not look at it right now, but simply it's a ratio that it compares the throughput of a given system to the average delay of the given system, right. So this is throughput is the benefit, delay is the cost, right. So it's a benefit to cost ratio is what you're trying to compare, right. So you would like to have a system which has high throughput and low delay, which means the power value will be higher, right. So because you will often find that there will be two algorithms, one which will sacrifice is always the delay throughput trade off is always there, right. So when you want to compare this kind of trade off, then you would like to look at some other metric, right, that might or might not help you, but really depends upon the system that you measure, right. I do not see power very often used a lot in today's papers, but that is another way of looking at it's an artificial metric, right. So these are all sort of natural metrics that we can think of, that is more of a concocted metric, right, that tries to combine different metrics together and have a single metric that will give you different views of the system as such. Okay.
Sir, when we are network is very congested, like we are dropping for packets, we can altogether drop connections also.
Yes.
So we can have something like percentage of connections dropped.
Yes, you could do that. So this is your probability of dropped connections. That is an extreme, but that requires some information in a typical IP flow. You will not know what is a right that these are packets going from the source to the same destination. If there is some other MPLS label and so on, where you say that I am going to ignore all packets from this particular label because it is used too much of capacity, or right some VC ID or flow ID is there, then you can do that. Otherwise, simply based on the source address, you will not know. Even source IP, destination IP, you need to know the port numbers also, right. So just a tuple that you have to look at, 4 tuple that you look at before you start dropping connections. But anyway, in theory you can do that if you want to differentiate, right. You won't want to have one particular connection which is overwhelming the network and sending too many packets, then you would like to drop those particular connections and so forth.
But that can happen only at the source router, right? You cannot
Even
have
intermediate
connection
routers,
to
if it's a label, right,
Yeah,
you look at the
MPLS
label and then simply say for now I want to drop all packets from this particular connection. It is like your red, what red does,
Yes.
right. Red can also do that, but red has a probabilistic way of dropping packets at a time from the queue, but you can simply say that I am not going to forward packets at all. I am not sure if it is used anywhere, but in theory you can do that, right. And then the forwarding table say that all packets from this flow for the next 1 hour I am going to ignore, either because of firewall reasons or whatever it is that you think that this particular connection is taking too much of resources, then you can use that as a reason to temporarily block the connection, right. And that will lead to upper level connection drops anyway, right. Yeah, so other things you have not looked at here is utilization of the link themselves, right. How are the different links utilized, because one of the implications of congestion control and of routing is, right, if I route all the packets on one particular segment of the network and the other part of the network is left unutilized, then you have high utilization over there but fairly low utilization on the other side of the network. So that is again not desirable, right. So utilization, load balancing of right resources used, all those things are there. So one can look at right per link utilization is there, and ideally you should be using all the links uniformly, but depends upon the traffic flows in the network, so there is no real control over that. But within these different algorithms you want to see if one is better utilizing the networks in a more load balanced way than other algorithms.
Anything else? In generic, any source like buffer or CPU.
Yeah, so you can look at average, that is why the queue length, right? Queue length is also another metric that is more of a finer grained metric that you want to look at. Sometimes you want to explain why some delays are happening, then you go look at that as a secondary metric to say, okay, here is the queue length distribution, and for this particular algorithm the queues are very long and therefore it ends up in higher delay. So that also we can look at inside the router. Yeah.
Important factor for congestion control, right?
So they use it to make decisions, you are saying.
Yeah. If you look at the red uses queue.
Red uses queue length.
RAM uses queue length.
Yeah, some that is actually an input parameter to the algorithm itself. In other cases it is not. So where it is applicable, you would look at queue length distribution. Okay, I think we can go further, but we will stop. We can say what is the impact on quality of service, right? Because we have not really talked about how do these algorithms differentiate with respect to different QoS requirements and so forth. So that is essentially what you would like to do. So when you sit down and look at a system, right, go through the system in detail, then always just looking at throughput and delay are just one metric, right, and that is basically not adequate. That is what this exercise tries to tell us. Okay, there is a section on common metrics, response time, throughput, bandwidth and so on, which I think more or less we have covered with this example, so I will not go through that section. There is one last section in this chapter which is on setting, right, performance requirements. So sometimes when you define a new system to be built, right, you would like to specify some in terms of, okay, this should be the number of connections, this router should be able to handle so many connections, or this algorithm should be able to handle such a large input size, right. So those are specifications that one writes, and that is used as a basis for the implementers, right. If you are sitting in a company giving a contract to some other company, you should be able to tell what your requirements are, and you can be very vague on those things. You can, yeah, this should run well, run very fast, right, those are your typical requirements, runs fast with least amount of resources, and then you just give that to the client and the client sits and breaks their head over what does this mean, or they interpret it the way they want, like this is the best we think is fast and so on. So it is easy to be vague on those specifications, but what this tries to tell you is that when you set the requirements, right, so these are things that we measure from a system as to what is the effect of it, but sometimes you want to just set some goals for your system before you start telling somebody else to actually go and build that system. And right, so some of the bad examples or poor examples, right, should be resource efficient, right. So the resources can be CPU, memory and so on. Or it can be even vaguer by saying extremely low, let us say packet drop probabilities, right. So these are things that you would rather avoid, right. And these days it is fancy to say everything should be energy efficient, right, whatever that means, energy efficient this, energy efficient that, green this, green that, and whatever that means we do not know, right. Is it going to be 10% lower than current systems, right. If you want to define a new whatever, right, vehicle or battery and so whatever it is, should be able to come out and say it should be less than, current consumption should be less than about 10% compared to your current systems. Okay, so that is why the author has put together this so called, right, smart set of requirements. So your requirement should be very specific, right. In some cases you can be very specific, some cases you cannot be very specific. Okay. So in the case of voice packets, right, that is sent on your voice VoIP or or even video streaming, right. When I send a packet, it should be delivered, we know there is some amount, some delay that is there, right, 150 milliseconds approximately before this, after which the packet is basically useless. So be very specific, right. So example, right, delay less than 100 milliseconds, right, one can say that, but that is still not very specific if you think about it. When I say delay less than 100 milliseconds, what delay? Average packet delay, right, or worst case packet delay, because worst case packet delay can be very large. I may say average is 100, worst case could be say 2 seconds or so, and these things are easier to specify than realizable, but anyway you should have, there is a, right, some fine balance we have to tread there. So it should be specific with something and also something that is measurable. So measurable, right, that is important. If I tell delay, I can measure delay and I can tell you, see, in my experiments I found that delay is less than your limits consistently, right, most of the time, or 90% of the time delay is less than 100 milliseconds, and therefore I have met your requirements. And if you are not specific in your requirement, then measuring is also going to be very hard. Sometimes the user may be saying that very easy to use, right, how do you define easy to use, you do not know. And even if you look at your voice over IP calls today, right, there is something called mean opinion score, that is actually also almost subjective evaluation, it is a subjective criteria than objective one, but you know that is about the best that we have today. So it is measurable, but it is kind of vaguely measurable, right. How do you define quality of voice on a VoIP call? Okay, you say your landline is 5, right, crystal clear, therefore that is 5, and your cell phone is about 3, right, and these are again not really measurable. It is not directly taken from your signal to noise ratio measure, it is more or less what people say that, yeah, I think this is good enough and so on, right, as to how you would rate your songs in iTunes, right, your 1 to 5 stars, you can call it measurable, but it is more of very subjective criteria, right. Then acceptable,
We need to put some range. or
yes,
some
yeah,
values
when you
to
set the
follow.
requirements of a system, yes, one is simply measuring. So for example, queue length you may not be able to say anything, but you would want to say queue length keep it always under 50%, right. If you say queue length under 50%, then it means that your link capacity should be higher, right, basically you should not operate the system at a load which will lead to more than 50% of queue length, right. So some of it depends upon your input and input parameters for the system also, right. So that is in terms of design of the system itself. If I want to design a system where the queue length will never be more than say 500 packets, you have provision for 1000 packets, but you want to make sure the system never really operates at more than 500 packets in queue length, then that is you have to provision it by controlling the load or controlling the system parameters, by saying that I would, the system parameters is what says, right, I have 1 gigabit per second link or 1 megabit per second link, where the workload parameter, these two things you would control to make sure that these requirements are met, or you will tell a set of operational parameters that says if you are within these ranges, system will have these kind of metrics. Yes,
something like making the technical QR of a
document. Yes, yeah. Those, if you are in military, you probably would know that, right? You have seen that when you write your RFPs and so on, where they say that, right? The system should support 10 Mbps of traffic, and that's all it will say. And like, what is it? Where does it come from? That is not always specified. Then we'll have to go and guess how much of it is voice, how much of it is data. If you say delay should be less than 10 milliseconds, then it is not possible for all kinds of traffic to get 10 milliseconds. Sometimes that is comes later, right? So when you build systems for customers, and you could say call drop probably should be less than if you're building your system that is delivering, supporting say your cellular network, right? And they say there should be no more than 1 call every million calls dropped when a user tries to make a call. Okay, that is good, well and specified, right? That's where some of these, it is yes specific, it is measurable, is it acceptable and realizable, right? Those are some things that you'll have to and thorough in the sense that you should be right, you should consider all kinds of metrics that make the system essentially complete in various aspects. Okay, so this is your first 3 chapters of which is part 1 of the textbook, right, more of generic setting the stage for what we would like to do, right, in terms of what are some of the expectations and so forth. Questions? Okay, I will. Acceptable to the customer, acceptable to the one who is going to implement that, right? Both, yeah.
When I have given realizable.
Yeah, I know, acceptable, realizable are a little bit confusing. I went back and checked if there is a better explanation for that. There isn't, so we will defer that and come back to that in just a second, right? We will just look at realizable is yes, if you are going to set realistic goals, right? Acceptable, we will come back and clarify on that. Yeah, whether the goals are achievable or not. Yeah. Acceptable also seems to be the same thing, so we will come back.
So acceptable depends upon the client's whether he is able to accept it or not. If you propose something, he is able to
Whether okay, yeah, that's possible. Where
it may cost more to the client.
But in the yes, but it
minimum
depends on who is defining, right? If the client comes in and says, "I want a system to support 1 million customers," then the client will accept that. If you give anything less than that, the client is not going to accept that. But you as a developer should know, a designer should know that this is actually achievable or not, right? That's where realizable comes in. Yeah, that's I guess just to have the acronym probably acceptable came in, but anyway, we'll take a look at that and deal with it later. Okay, part 1 khatam, so we move to part 2 now. So the book's part 2 is not our part 2. I am sort of going out of order with respect to what the book is trying to do. In fact, the book, whatever I want, is in chapter 29. Okay, some part is here, some parts are elsewhere, so there will be a little bit of jumping in the book, but because this book is more of a reference. Sometimes it is textbook, sometimes it is a reference. There are some chapters that we simply can directly go into the chapter without looking at some of the previous chapters. Okay, so now we are going to start looking at techniques, right, tools that actually help us look at the mathematical modeling of things. So that is part 1, right. We said there are 3 different techniques, mathematical techniques as well as simulation and implementation. So we look at some mathematical techniques that will help us understand analyze the performance of some subsystems, right, and that will not be exhaustive. You will not know all the possible techniques. This is more like CS 110 or basics of programming, right, where you know some basic amount of programming, but as you look into more and more research articles, and if you keep following all the performance magazine or performance conferences and journals, you will find that there are more and more performance evaluation methodologies that keep coming out. So for now we will look at the most common ones, right, that can help us figure things out. So we will start off with looking at Markov chains and birth-death processes, but before I go there, I think we need a brush up of some of the basics of random variables and some of them commonly used variables. Okay, and again our statistics and probability, little bit of that we will try to do.